Okay, so having established Newton's law of universal gravitation, which is F equals G, I'm going to use the big M little m version this time, but anything's fine. G big M little m over r squared. What I want to look at now is how we can use that to find one of Kepler's laws, Kepler's third law, in fact, which says that if you have two bodies orbiting the same big primary body, then there's going to be a certain relationship between the radius or the radii of their orbits and the period of their orbits. So let's set up our little sun here, and let's say we have planet 1 at radius 1 in its circular orbit, which takes a period t1 to complete. And then further out we have, I'll just use round to be slightly different. Or actually, let's not do it there. Let's do it over here so it's a little bit off. And then this goes around, yada, 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 yada. Okay. And, well, ideally it actually comes back to the same point in a circle. Pretend these are circles also. Okay. So there's R2. So what we want to do is we want to find some relationship between the period of planet 1, the time it takes it to go around the sun once, and the period of planet 2, which is the time it takes it to go around the sun once. Okay, so first of all, what we need to do is take this equation, and I mean, you guys have, this is just what we do pretty much every time we have a circular motion problem. Is it always seems to come down to solving these circular motion problems always comes down to finding acceleration, matching the acceleration, find the acceleration two different ways, match them up, and solve. And in this case, we use F equals ma to find the acceleration of our little thingy here. So if little m is the mass of a planet, then this and big M is the mass of the sun. So mass big M here. Let me make it bigger. Make it actually a big M. Mass big M there. Mass little m is like a planet, and r is the distance from the sun to the planet. Then this is how we find the acceleration from gravity. And so what this gives us, of course, is acceleration from gravity is equal to capital G times big M over r squared. And the little m just cancels out from both sides because we're setting both of these equal. You can see that. Okay, so we apply this to each particular one. Well, first of all, let's say what happens if we have a, so this works great here. And this also, for circular motion, we have, well, this is for our, for gravity. For circular motion, we have A equals V squared over R. Okay. And since we know that V equals 2 pi R over T, done this a billion times. You had test questions on this. We get A equals 4 pi squared R over T squared. And I hope really hope I'm not off the edge of the screen there. So that's what we get. So we want to set these two equal. So this is the acceleration we get from gravity. This is the acceleration we need to keep our circle. And so this is going to be equal to G capital M over R squared. And what we get there is acceleration. So this is, right, these are both equal to acceleration. So we don't need acceleration anymore because these are both equal to acceleration. We set them equal. So we want to find a relationship between the distance this planet is from the sun and the period of its orbit. And well, there's our T and there's our R, which is radius of the orbit and period. We've got those. So what I'm going to do is pull all of our R's and T's over to the right-hand side of the equation and shove everything else over to the left. So on the top here we have GM, that goes underneath here. So what we're going to get is 4 pi squared over GM. So that's this and this. And then we bring our R over and put it underneath, and T squared over R cubed. It's probably a little more, I don't know. It might be a little more normal to write it as GM over 4 pi squared equals R cubed over T squared. I don't know, one or the other. But it doesn't really matter which way you go. The point here is that for this system here, this solar system here where we have two planets, the sun, everything on the left is the same for both planets because this is the sun's mass, right? Capital M is the sun's mass. G is a universal gravitational constant. That's the same everywhere. and then you have 4, which is the same everywhere, and pi, which is the same everywhere, squared. So this on here on the left, and this is what Kepler said. See, Kepler didn't have the big G and the big M, and he had no idea what this side actually was. But what he found out was that it is constant, provided it's the same primary body at the center of your system. And actually, well, the only one he had to look at, the only system he had to look at was the solar system. So, the only thing he could do was different planets orbiting the sun. But he found out that for all the planets, if you took this r cubed for each planet and divided it by t squared, where r is the radius of the orbit and t is the time it takes the planet to circle once, then you get a constant no matter what. So just to go up here, I'm going to say, I happen to know offhand, because I was an astronomy geek when I was a kid, that the radius of Earth's orbit, which I'm going to call, let's call it little r sub e, the radius of Earth's orbit is, let's see, it's 93 million miles, which means it is 150 million kilometers. So it's 150 times 10 to the 6th. Actually, we don't even need that. I'm going to write 150 million kilometers, okay? So, and we know period of the Earth's orbit is 1 year. Now, I happen to also know that the period for, I don't know, what planet should we do? I'm going to do Jupiter, because I think I know that. I've been getting all these wrong, though. Like, every time I pull a constant, I'm out of my butt for one of these videos, it's always slightly wrong. So, but I think Jupiter takes 11.2 years to orbit. Boy, is that right? That sounds about right. Maybe if you're in astronomy, you'll totally correct me. But so what we do simply, if we want to calculate the radius of Jupiter's orbit, which is what we want to find here, then what we do is we say that so r cubed over t squared is a constant, right? So what we do is we say radius of Earth's orbit cubed over the period of Earth's orbit squared is going to equal a constant, and that's the same constant that rj cubed over tj, okay, tj, got it? Tj squared is going to be. So in theory, let's see, what we should do is we want to find radius of Jupiter's orbit, right? So we're going to take, let's see, where's some space I can write in? Let's do it. I'll do it in purple, and I'll do it down here. So if we want to find radius of Jupiter's orbit, then radius of Jupiter's orbit cubed is going to equal, let me just do a little ratio here, radius of Earth's orbit cubed times, and this will be tj over te, and I'm just going to do the group squaring thing, okay? So this should give us the answer if we plug it in. So I'm going to try this, and let's see. So Earth's orbit is 150. I'm just going to use units of 1,000,000 kilometers, so I don't even have to worry about typing in million, or converting to meters, because see, this equation here is just ratios here, right? So as long as you have the same units everywhere, doesn't matter what they are. I could use what's the old joke, furlongs and fortnights, and it would still work. Okay, so there's my 150 cubed for the Earth's orbital radius cubed, times, let's see, and then we're going to put this in parentheses, so I want tj over te, which is going to be 11.2 squared. So there's my ratio of Earth's orbit to, or Earth's period to Jupiter's period squared. And then what I want to do is take the cube root of that. So instead of doing cube root, I'm going to multiply. I'm going to take the 1/3 power. That's how it works, right? Yeah. Okay, and this should give us the radius of Jupiter's orbit, which is 750 million kilometers, which is about almost exactly. Oh, it's interesting. Almost exactly 6 times the radius of Earth's orbit. That actually makes sense. Because I think Jupiter's like 4 times as far out as Mars, and Mars is like maybe 50% further out than Earth. So if Mars is 1.5 times as far from the Sun as Earth, and Jupiter is 4 times further than that, or 4 times as far as that, then that should mean Jupiter's radius is, oh wait a minute, no, it's only 5. Oh, 750 over 150 is 5, so I don't know. I'm probably a little off here, whatever. it doesn't change. I mean, look, Kepler's right. I'm wrong. Okay, don't take this as a disproof of Kepler. Kepler was right. I was wrong, and Newton proved that Kepler was correct. That's all I got to say about that.